So Yasin will present on the part of iThEC, the International Thorium Energy Committee, the committee which organized this conference, his vision, or the vision of iThEC as to what can be done with thorium. And Yasin is well known for speaking on this subject. He's attended numerous conferences in the past. So Yasin, over
Thank
to
you, Mr. Chairman. Good morning, ladies and gentlemen. So I would like to present you some of the objectives, basically, of the iThEC association, which has been formed quite recently. So the approach that we have with respect to nuclear waste transmutation and energy production utilizing thorium as a fuel. So the main concerns, you all know, these are related to accidents, safety concerns, nuclear proliferation, the utilization, or I would say the depletion of the known uranium resources, and the accumulation of nuclear waste. These are mostly the concerns, the items that we are concerned about within the association. And we also think that unless these problems are solved, it will be very difficult to enable to deploy nuclear energy on a large scale. Looking at the path towards sustainability, what we see is that if we consider that for the next 40 years, basically the current nuclear power installation will only double, so going from the currently existing installed 400 gigawatt electric to 800 gigawatt electric, then of course this would mean that it would be a very small, or there would be no incentive basically to go for advanced nuclear fuel cycles. So the open fuel cycle will just do the job as it is doing right now, and this would be a sort of business as usual. On the other hand, we have seen from the presentations and the policies of the different countries, in particular in Asia, that by 2030 we are looking at the prospect of almost tripling the installed nuclear power capacity, China alone. So if you add to this India, that would probably by 2050 almost multiply by almost 10 the installed nuclear power capacity. In this respect, an accelerated alternative scenario has to be found. And this could only be made possible by closing the fuel cycle. So I think there is clearly, how do you say, a consequence from this is that the research, R&D, and also all the advanced systems and nuclear fuel cycles will have to consider this aspect. So closing the fuel cycles, of course, means finding ways to manage the nuclear waste which will be accumulated, and also generating in a sustainable way nuclear electricity. In this respect, within the International Thorium Energy Committee, so we are striving basically to develop or foster an international initiative or collaboration on a large scale in order to promote the realization of a demonstration of a thorium iThECs by 2030 in order to provide at least a possible solution for addressing this accelerated scenario. The role of iThEC, so our key objective is to encourage the transmutation of nuclear waste and thorium power generation. These are our two leitmotifs within the association. Our actions basically are in the form of organizing conferences, and I think this is our first milestone that we have achieved this month. Addressing as well political and economical circles, the media and the public, and fostering links between academia and the private sector. Concrete steps that we have taken, so association was founded as a non-profit organization based in Geneva in September 2012. We have organized the conference, as you see. And by 2015, we are aiming to set up an international collaboration for an iThECs demonstration iThECs for thorium power and waste transmutation. So when we talk about transmutation, of course, we refer to partitioning and transmutation of the TRUs. So these are mostly the plutonium and minor actinides, but also the long-lived fission product. It should be kept in mind that in the case of plutonium, for some countries, this is considered as a valuable resource, and for others, it is just part of the waste. However, these partitioning and transmutation technologies must apply to all fuel cycles, and this includes also the molten salt system, if it has to be sustainable. So you can see here the potential that PNT would introduce in the reduction of the of the radiotoxicity of the spent fuel, where we could achieve basically almost 3 orders of magnitude reduction in the health, in the radiotoxicity of the remaining waste. How to deploy this transmutation part? How to deploy transmutation or partitioning and transmutation in the different reactor scenarios? So one scenario, of course, would be to basically have the accelerated deploy minor actinide burners to basically handle whatever waste generated by the installation or the operation of Generation 3 and Generation 4 fast reactors. iThECs basically being the only solution for the minor actinide elimination, whereas plutonium would be handled basically recycled in this scheme. This is what is mostly referred to as the double strata stratum scenario, and which is a scenario which is being considered, for example, in France, and was considered in Japan. I don't know if it's still the case today. In such a case, the minor actinide-based iThECs would be a very efficient system in order to transmute the minor actinides. We could go up to 50 kilograms per terawatt hour, depending on the type of fuel loading, so pure minor actinide cores, minor actinide minus curium, so where the curium is basically put on the shelf. This enables us to achieve very deep, very high transmutation rate. So what you have here, sorry, probably you cannot read this very well. So transmutation rate in kilogram per terawatt hour thermal. And here you have the different fuel types that could be considered. So these are pure minor actinides. These systems, of course, enable very high transmutation rate to be achieved. However, it would be very difficult to control from a reactivity point of view. One of the particular aspect of burning minor actinides alone without a fertile matrix is that the reactivity of the system increases with burn up. So basically, minor actinides are very good for breeding new fissile material. So you can see basically also the disadvantage of having these systems basically in critical or near critical systems. Topping the fuel, the minor actinide fuel, or enriching the minor actinide fuel with plutonium would enable basically to more or less control the reactivity, stabilize the reactivity of the system over the fuel burnup. In such a way, another possibility, of course, would be to basically already start with in the first stage with an iThECs systems, where the backlog of the nuclear waste could be utilized basically to initiate the thorium fuel cycle. So by burning the waste in a thorium-232 matrix, basically one would breed uranium-233, which could then be injected into the light water reactor fleet as a replacement for U-235. In such a consideration, one would already gain quite a lot in terms of utilization of resources and basically eliminating the need for uranium-235 enrichment. This would also reduce the waste which is generated in this stage. If you look at this type of systems, you can see that by basically loading in a thorium-driven ADS, one would achieve very high burn-ups for plutonium. But one could also consider, in the blanket of these systems, to incinerate the long-lived fission products. And you can see here the rates which are achieved for both technetium-99 and iodine-129, the two isotopes being responsible for almost 90% of the volume of the waste which is to be deposited, to be basically buried and deposited in the future. As you can see, one such system could, these are transmutation rate expressed in kilograms per terawatt per unit energy. So basically, such a system could already handle the production or the waste which is generated by about 4 or 5 PWR. So it's quite efficient. So every 5 PWR, basically, you would need such a system, basically, to get rid or to handle the nuclear waste generated. An interesting point to mention here is the discrepancy that one would find between the utilization of the different nuclear data libraries. So which means when you develop or when you study these scenarios, one should be very careful to the type of nuclear data that you use and the method which is being used. So there's still quite a lot of work, but we have seen in the conference that a lot of new results and a lot of progress have been made in terms of improving the status of the nuclear data, in particular at NTOF here, our NTOF facility here at CERN. What is interesting as well is that in those type of fuel configuration, what could basically tune the variation, so the reactivity swing of the reactor. So this is the variation of the reactivity along as a function of burn-up, just by basically selecting the correct, adapting the concentration of plutonium in the thorium fuel. Increasing the plutonium concentration basically will just result in a core which is constantly burning the fissile material at a very high rate, but the reactivity will be dropping constantly, and this should be basically mitigated by increasing the intensity of the accelerator current in order to maintain a stable or constant power output. But varying or reducing this concentration down to 12% of the total fuel mass, one could basically achieve over a very high burn-up up to 100 gigawatt Dayton, a relatively stable K, without diminishing, therefore, the need for a higher intensity accelerator. If you consider such a system, basically I would like to come back to the 3-stage program, which was extensively talked about in this conference, where basically the implementation of the thorium and uranium fuel cycle in the ultimate stage, so stage 3, which is in the advanced heavy water reactors, basically rely on a constant production of fissile material through both the stage 1 and stage 2 systems. With the system that we are proposing, so basically deploying already in stage 1 an accelerator-driven system fueled on thorium, one would in principle eliminate the need for these two first. So here, the accelerator playing the role of providing basically the fissile material which is required for driving the third stage. Fissile material in terms of bringing uranium from the nuclear waste stockpile, existing stockpile, or just the plutonium stockpile as well. Now we know that development of these type of systems or advanced systems takes quite a long time. You have here a chart of the time it took basically to go from the first generation to the generation 3+. So on average, it's about 20 to 25 years per generation. So we hope that if we want to be ready by 2030, so basically a lot of R&D and has to be already done or be carried out for that. Unfortunately, in the case of the accelerator-driven system, what could rely on systems which have already been tested and which are available. And for example, for a demo, I'm talking here for a low-power demo, what could already make use of the very efficient and one of the most, actually the most powerful accelerator which is in operation today. So this is the 6590 MeV cyclotron at PSI, with almost operating at above the 1 megawatt, so 1.2, 1.4 megawatt of beam power. So this would already be sufficient to drive an accelerator demo. In terms of spallation target technology, so we heard about the demonstration, or the very efficient demonstration of the ability or capability to operate a 1 megawatt class, spallation target. So this is basically was shown as MegaPi. In terms of reactor technology, fast reactor technology cooled by lead bismuth, one could rely on the extensive work and operating experience that the Russian had with this type of systems, of course, as a critical reactor. These were reactors installed in their nuclear submarine fleet in the last 30 or 40 years. So. And in terms of reprocessing, for closing the fuel cycles, I think there is a major advantage, basically, that we see in utilizing the pyrochemical reprocessing scheme as opposed to the aqueous scheme, in the sense that one could enable, with such a system where a lot of neutrons are available for transmutation, to recycle not only the minor actinides, but also a proportion of the fission products and lanthanides, which could be easily extracted from utilizing this scheme. This would enable to basically complicate the reprocessing scheme by having different separation methods for the different isotopes elements, making the nuclear fuel the waste. One could rely also on the extensive R&D which has taken place in Europe and in other parts of the world. And these have basically, as we have seen, targeted most of the technologies involved in the iThECs. So target technology, subcritical core physics and technology, fuel technology, accelerator technology, and also core design. So these were shown. I would not like to go into details. One also can rely on the large-scale facilities which have also been developed in the last 15 years to study the material compatibility aspect of these different materials. Lead bismuth, lead loops are in operation, and quite a few of them in Europe, but we also now see that similar installations are being operated, are under construction, or even in operation in Asia, namely in Japan, India, and China. So the programs, of course, also we have heard about the few programs or systems which have been proposed or which have taken place. Just to name a few, you probably heard about the very first experiments that were carried out at CERN, basically to demonstrate the feasibility or the principle, proof of principle of this energy amplifier systems. This was followed by a series of zero power or very low power reactor physics experiments sponsored by the different research programs in Europe, but in also worldwide. So the Muse experiments in Cadarache in France, the French Atomic Energy Commission. The Yalina experiment in Belarusia. I think it's an experiment which is now being repeated in India, as we've seen from the last talk. So the Purnima experiment, so very, how do you say, easy, I would say, experiments to carry out in order to learn quite a lot of, to get quite a lot of information as far as the dynamic behavior of these systems. It would be good if at a later stage, probably Purnima could be converted to a fast system, because I think this is where most of the physics is, dynamic physics, reactor physics is of interest. And we also heard about the MegaPi demonstration, the program in Japan, a program in Russia, SAD, which was cancelled, and also the MIRA project, which has been proposed and is now gathering quite a lot of momentum and is currently under design. In our opinion, I mean, such a demo would probably be developed in 3 phases. This is very similar to what has been proposed or retained in China, so by the Chinese Atomic Energy Commission. This would go from a phase 1 where basically the subcritical core will be operated with the very low subcriticality, around 0.95. This is not the optimal, of course, configuration for an ADS. This means that would put quite a lot of emphasis on the accelerators in terms of providing the beam current. However, this is a very effective, an appropriate subcriticality level to study all the safety aspects and reactor physics, reactor dynamics parameters of a system. This could be done with a very low, relatively low power proton driver, so 250 MeV, for example. These are already commercially available. Cyclotrons of this with this energy are commercially available. Of course, some work would have to be done in order to reach to provide 3 milliamperes of beam current. Gain, of course, is quite low, is below 1, but the whole idea of this phase is not to optimize the system in terms of neutron utilization or spallation source gain. However, the system at 11 megawatts or around 10 megawatts could provide already all the information which is required for licensing, for the licensing aspect of these systems. So all the power reactivity coefficients basically at 10 megawatt are already of the same order or very or almost similar to those of a high power reactor. This is one of the beneficial aspects of utilizing fast systems. For a thermal system, of course, this is not the case. In a phase 2, one would gradually increase or double the intensity and increase, eventually having gone through the safety optimization of the system, increase the K, the subcriticality level of the device up to the nominal subcriticality that we think is around between 0.97 and 0.98. And in this case, the system could already operate at about 50 megawatt, which is a system where this is quite a strong neutron source. So one can do not only fundamental research and reactor physics, but also could utilize these neutrons for many other applications. And I think material testing, isotope, radioisotope production is, of course, a very, efficient. This machine would be very efficient for this type of applications. In the third phase, these parameters would have been validated and fixed. One could basically increase the beam energy of the proton driver, so keeping the beam intensity intact, and envisage, so about 5 megawatt of beam power that could easily, and with the beam energy, the gain, of course, the efficiency of utilizing spallation neutrons would, of course, increase to its nominal value. And this would provide basically an overall gain of about a factor 100, which means a system capable of producing 540 megawatt of thermal power. Of course, this is a demo, basically, what we call the commercial demo for the deployment of this technology. With this power, basically, what could already think of transmuting on a large scale or demonstrating on a large scale the transmutation of nuclear waste. And we're talking here of about a few hundred kilos of nuclear waste or minor actinides that could be transmuted per year. So, all in all, the iThEC initiatives, as I said, boils down to aims at, by 2015, at setting up an international collaboration to build or think about the realization of such a demo. Just to remind you that our two objectives are, of course, transmutation of nuclear waste and thorium energy production. In the coming 2 years, the association will identify material and also financial resources and competencies on a worldwide basis. And we will invite interested parties basically to join in this common undertaking. So with this, I have still a few concluding remarks concerning the potential of accelerating driven systems to offer a unique level of safety, which guarantee, as I said, an operational flexibility for future systems, for future advanced fuel cycles, both for clean energy production and waste transmutation. The present accelerator technology offers the possibility of closing the thorium fuel cycle, and the energy amplifier is one of these examples with a very high potential. So iThEC aims to promote the deployment of these technologies. So with this, I would like to thank you for your attention.
Thank you, Yassine. Yes, there are already quite a few questions. We'll start with the nearest one, maybe, and if we can find a microphone. And then we'll pass on to... we have a lot of questions, so we'll pass on. We'll have 1, 2, 3, and then 4, and then, who knows, 5. But first of all...
Yeah. No, I just want a clarification. Your figure gave an impression that you're using just plain thorium and waste. You are obviously talking about K-effective 0.95. So what is the fissile content?
No, the K-effective can be adapted as a function of, by playing with by adapting the concentration of the waste concentration in the thorium matrix. So for me, waste is, in this case, in these calculations, is mostly plutonium and minor actinides. So really the spent fuel waste stream. So
you're talking about plutonium, thorium, and minor actinides.
So thorium with spent fuel. So which is plutonium and minor actinides, correct.
Yeah. And then you're talking about spent fuel to get into molten salt through some processing routes.
It's not molten salt.
It's, what's
so
the
these
fuel
are solid fuel, oxide fuel.
Solid oxide fuel.
Yes, yes.
Then you're talking about separating plutonium and mixing with thorium.
No, so the idea is not to separate. So the idea, I'm sorry, it's just coming back. So here, the type of fuel which is used is thorium-plutonium oxide fuel. When I say plutonium, I mean dirty plutonium. So it's plutonium with its minor actinides.
No, I understand.
Yes, yeah.
But you have plutonium in the spent fuel.
Yes.
Uranium, plutonium.
Yeah.
You want to separate plutonium and mix it with thorium.
So the first step would be, of course, to get the uranium from the spent fuel.
You're obviously getting out uranium from this, is it not?
We're breeding uranium-233, absolutely.
No. I'm talking about the uranium from the spent fuel, current spent fuel.
Yes, so you would basically reprocess the spent fuel in order to extract the TRUs,
okay.
Plutonium and minor actinides.
That's
so no uranium.
That's exactly what I wanted to be clear about. Yeah.
Yes.
Right. Okay, next question.
No, because you put cross on first stage and second stage. So
correct. Provided that you have spent fuel already.
The gentleman in the middle there. The gentleman in the middle there, I think he was first, and then this gentleman. No. All right, whatever. So this one and the next.
Kadi,
you'll be next. Okay.
I'm sorry, please talk up. I can't hear you.
I'm getting a bit confused based on your presentations, What I understand, you are presenting on behalf of this International Thorium Energy Committee.
Yes.
It's not a science or technology. So my confusion is that what you are really promoting, you are promoting thorium as an energy source for the sustainable development of energy, or you are promoting iThECs for use of thorium?
No, we're promoting basically the implementation of thorium as a source of energy production. And I would defy you today to tell me that you have a technology which is ready to accept thorium on a sustainable way. And for us, with all the studies that we have been carried out, clearly the iThECs provides the neutron inventory, basically the flexibility to be able to use these advanced fuel cycles that we need.
Exactly. That is a science. That's
yes.
not the technology.
Yes.
But there are, if you see the Generation 4 reactors, there is a projections between 2030 and 2040.
Yes.
There will be a number of host reactors.
Yes.
Not only for the number of host reactors for the user, there may be a dedicated burners
Correct.
for the transportation of these monoactinides.
Yes.
Now, if you compare the economics part of it, of partitioning and transmutation, particularly in a dedicated burner or in an iThECs, how the iThECs stands, where it stands. The economic aspects of burning, transportation of monoactinides in a dedicated burner in a critical system, either in a homogeneous or heterogeneous mode, and the transportation in iThECs.
So I believe it would be very difficult to basically handle all the minor actinide waste with the Generation 4 systems. You alluded to that. If you load this in the homogeneous, in the homogeneous way or heterogeneous way, it will be still the transmutation efficiencies will be relatively low compared to what I've shown for a dedicated burner. Now, remember, minor actinides are isotope with a very low beta effective. So any gram of minor actinide that you introduce in these critical reactors will deteriorate the safety parameters. Yes?
This has been demonstrated.
The safety parameters. So void coefficients and beta effective. So therefore, if you really want to get rid of the minor actinides waste in an efficient way and safe way, I think iThECs or dedicated accelerator-driven subcritical systems are the technology to be used.
Right. I think he was, the gentleman in the middle has been waiting for quite a while. Yes.
Well, tens and tens of questions and remarks on your incredible presentation, saying that you have found idle system which is clean, which is safe, which is, well,
Yes.
take care of this kind of presentation. Here it's okay. If you go out of this building, take care of this, because the people will discover that this kind of safety problem will not burn all the minor actinide. This is physically impossible. So you will need anyway a deep geological repository. Many things they will be discovered. And when the day they will discover that, we will be killed.
Yes.
Okay.
I think promoting the sodium technology today is also a killer. But I think this is the argument
I'm not
for you.
promoting sodium.
Yes. I know what you want to come to.
Wait a minute, sir. I
Yes.
didn't say that.
No, but
I didn't say that.
I never mentioned that we will basically replace eliminate the need for deep geological repositories. I gave you some transmutation rate figures, which are the result of simulations, of course, and hopefully will be demonstrated. And from these figures, you can see that we're almost eliminating at the theoretical limits the minor actinides and the long-lived fission product. So it's very clear. When you take this into consideration, you can calculate yourself what is the impact on the radiotoxicity and the reduction of the volume of the waste, and what is necessary to be deeply, put on the ground. Now, I would like you to show me what is the type of transmutation rates that you can achieve for the minor actinides with this type of systems. And we can compare. It has been a study by the OECD. It has been compared. And one of the conclusions is that this iThECs, of course, this is why France is proposing or promoting this double strata.
I'm not promoting. I am not in a religion,
I'm not in a religion either. I'm not in a religion either.
I am not representing a church.
Yes.
The NEA studies published in 1999 and then 2003, the main conclusion, I just read it before, is that both systems has almost equivalent performances, recycling, particularly americium in the blanket of fast breeder reactor. The iThECs has no much more.
But you would have an impact on the safety parameters of these machines. And this you cannot deny, because as you correctly said 2 days ago, physics is physics.
Yes, thank you.
So when you recycle minor actinides with the beta effective of 0.2% and with an impact on the void coefficient for these systems, guarantee me that you can improve the safety by utilizing those.
I don't want to monopolize, but just one point. go to the iodine 129. Please
Yes.
come back. You are going to transmute iodine 129.
Yes, in the blanket.
Where will you find iodine 129? It no more exists. Do you know where it is?
No.
Where it is?
Vitrified.
No. In the release, in the normal release
Fine.
of the reprocessing plant.
Yes.
So why do you put this one?
Because if you consider the scheme that we have proposed, which is based on the reprocessing or the pyrochemical processes, basically in this stream, one can consider, instead of letting the iodine to volatilize in the atmosphere, consider to recycle this.
But
And we have made a test, an experimental test of this with lead iodine, and it transmutes very well.
Today, you are trying to transmute something that doesn't exist.
No, but it could. If you apply the complete fuel cycle, I'm presenting a fuel cycle. So in this fuel cycle, when you operate this system in thorium, the iodine, if you apply the pyrochemical processes, could be re-injected in the system. I'm not telling you what I'm going to get rid of. If you have already got rid of the iodine, good for you. I'm telling you for the future, for those people who will install 8,000 gigawatt electric, this system is proposing a solution for taking care of the iodine and the technetium that will be accumulated then.
What about cesium-135? It is impossible to transmute it?
We haven't looked at this in detail, of course. You will have to isotopically separate it from the 137.
When you try to transmit, you produce more cesium than the...
You can, I'm sorry, I'm not here to answer. I mean, we can go through the whole list of Mendeleev table if you wish, but okay.
There are 7 long divisions.
Yeah. Yeah, I know,
Yes.
I know, thank you.
Right, we'll stop at this, and we'll continue with the gentleman here who's been waiting for a while.
My question is, to achieve that goal, do you rely on existing institutes, or would you create a kind of CERN-like institute?
No, absolutely not.
To do
We
that?
rely on partners, because the technology is within the partners. So technology already exists within the different partners, and the idea is to bring those people together towards one common objective of goal.
But not geographically. You
No,
will
of
not
course
unite
not.
people
Of course not.
on your sensor.
No, as I said, I mean, a lot of people, a lot of installations and facilities are available throughout the world, which are basically developing or carrying out the R&D, which is necessary for this type. This is not one institute developing the whole system. I mean, we have to bring those people together towards a common goal. Yes, absolutely.
Right, Hamid? Sorry, and then the gentleman next to Hamid, or whatever. Yeah.
I think there was one very interesting question, was saying one has to compare the economical viability of the solutions.
Yes.
And I would like to say that we are conducting at the European scale within Euratom the ARCAS project, specifically dedicated to compare the burning or the transmuting of minor actinide in ADS solution, as well as in critical sodium reactor being in homogeneous or heterogeneous. And in this comparison, what we are looking at is indeed the whole cycle, because it is not simply the amount of megawatt you need and amount of kilogram you burn. It's also the separation. It's also the transport. And when you are transporting those products, I mean, it is costly, especially if you have 50,000 people lying on the railway that you have to avoid to kill. And so these elements are taken in this study. And we think that we will finish this ARCAS comparison by the end of this year, beginning next year. The results will be available and publicly available for everyone.
Thank you very much. It'll be very interesting. And
yeah, this is taken care, and also so the separation aspect is taken care, the transport, the specific fuels fabrication, all these elements are taken care in this study.
And the dismantling as well, for instance, you know how much it costs to dismantle Super Phoenix? This is also factored in.
Now, this we didn't take the dismantling because it is not part. This is for the facilities. I mean, that we don't take care.
Because dismantling something with irradiated sodium is quite expensive usually.
Yeah, okay, but I mean, don't ask for one study to be so global. We have already taken so much in this comparison. I think it is a reasonable one.
Yes,
can be complemented by other aspects.
Right. Are there any other questions? Yes. Sorry, I forgot. Yeah.
I think what you're proposing is a amplifier to supplement what's going on in the usual sense of things here. Generation 4 is coming with fast reactors, but you're proposing that we should put as an objective transmutation as a high objective.
Yes.
And that's what you should state, that this is a high objective for the industry and for future, that it should be, it should not be combined as it should be number one objective here, that that the industry should think about reducing the time for solving the waste problem by reducing the time it has to be put into repositories.
Cool.
Repositories are needed, but we are trying to go to reduce the time that one has to deal with. And then say that we can think of another system which is a supplemental system, this energy amplifier, and with subcritical core, that it would supplement the other system of reducing the actinides also. So this is not the only solution, it is a supplemental solution.
It's not only a supplemental solution, it is also a comparable solution. Because for the thorium, I still insist, for the thorium, bringing the thorium fuel,
bringing thorium is a good idea.
You need this system.
As I was saying on first day, that it's a good idea to bring a thorium also as a supplemental system, because we shouldn't depend only on one. And secondly, now what you should say that as an industry, as a societal objective, reducing the time to put these waste products in repositories should be a prime objective.
Yes, this is what number one here. Thank you.
Well, you don't say you don't mention the repositories. And
yes, well, it's here. Time is here.
Yeah.
Thank you.
Right. So we do still have a lot of questions. I'll try and take two still, if it's possible. So the gentleman then, and finally, and it'll have to be the final one. I'm sorry, otherwise we'll run out of time.
I saw in one of your slides that that you are trying to bypass the second stage and try to just have thorium breeders in the third stage. So with regard to the deployment of ADS for thorium utilization, if you have a K-effective plant at, let's say, 0.98 or 0.99, as we saw, then it's practically a critical reactor from the breeding point of view, and it offers no advantage whatsoever over a critical reactor. On the other hand, if you talk of reactors which are much lower in K-effective, they would have advantage in terms of breeding. So if we are going to expand the thorium program, you cannot do it without breeding, and either you go through the plutonium route as we are doing in India, or you have a bypass route. Suppose you want for utilizing thorium, then you have to have breeders which work at much smaller K-effectives, either in once through or in recycling modes.
I completely disagree with you, because there is a major difference between being critical and subcritical. So whether it's 0.99 or 0.995, as you say, because this, of course, subcriticality gives you safety margins. And these safety margins are very important, basically, in order to give you the flexibility in utilizing the type of fuels or the different fuels that you want to use. And it was shown as well, I think, by Jean-Pierre Revol, that the response of a critical system and a subcritical system to a reactivity insertion is very dependent on the subcriticality level and the response, of course. And the response, yes, it is. So we could probably go back to that.
Sorry, really, one last question. We're really running out of time. I'm sorry.
My name's Ed Pyle. I guess I disagree with having the transmutation even as a primary objective. The three big problems that we have in the reactor industry are, let's see, reducing the cost of the systems, getting rid of dispersive mechanisms in the systems, and eliminating the problem of decay heat. Transmutation is not really a big issue, and criticality is not a big issue. We simply don't have problems with criticality, and that adds to the cost of the overall system. So, and that's a large factor in maintaining reactor systems. As far as transmuting systems, the building that we are in right now is probably large enough to store the entire amount of minor actinides that we have in the entire world. The half-life of minor actinides is 10,000 years. You can bury all of Geneva in toxic waste that have a half-life that's infinite. So I don't really see the issues associated with going to an ADS system that increases the costs and gets rid of two problems that aren't the major problems in the nuclear industry.
Well, I'm surprised to hear this from you, but okay, this is the point of nuclear industry, that you're not worried about nuclear waste and proliferation or aspects or whatever, plutonium, yes, because you have to transport. So this is...
I am interested in elimination of nuclear waste.
Yeah.
But I think the general way of getting rid of waste in the first place is to not produce it, not to focus on creating it to be able to get rid of it.
Yeah.
So
however, here in Europe, we have a different situation, that we have nuclear waste, and it is a societal issue, and by law. So there was a law passed in 1990 where we are obliged to look at what to do with the nuclear waste, and that includes deep geological repository and transmutation,
so
partitioning and
it's a political
transmutation.
issue, it's not a technical issue.
It is a technical issue. I would defy you to transmute all this waste in the present systems.
Right. So that was a very interesting and lively conclusion to the whole conference. Last talk in the series.